What happens after death? When life's final moment arrives, every culture, tradition, and individual harbors a different expectation. Some envision a journey to a spiritual realm where deceased loved ones await. Others embrace the idea of reincarnation, an endless cycle in which we are born again in various forms and with different purposes. Still others assert that nothing remains once the final heartbeat stops, only an eternal silence and the total absence of experience. Although these positions differ, they share a common root: uncertainty. Beyond any religious or philosophical stance, science views death as the cessation of vital functions. The heart stops beating, neurons lose their oxygen supply, and brain activity comes to a halt. However, that outlook describes only the physical aspect of death without offering a conclusive statement on whether there is something beyond the body. Even neuroscience research into the final electrical discharges of the brain cannot confirm if consciousness continues in some fashion or vanishes entirely. One element fueling the debate is near-death experiences, reports from those who were clinically dead for seconds or minutes and describe tunnels of light, an intense sense of peace, or encounters with deceased relatives. Medicine typically explains these episodes as chemical or neurobiological responses of a brain under extreme stress or influenced by medications and lack of oxygen, whereas others interpret them as indicators of a spiritual dimension or as evidence that consciousness briefly departs from the body. Matters become more complex when we consider diverse faiths. Buddhism posits that death initiates a transitional state, bardo, leading to rebirth. The Abrahamic religions speak of a final judgment and either heaven or hell. Other doctrines suggest a merger with a universal essence. None of these claims has been empirically proven, yet they powerfully shape human behavior. Many find solace in the hope of an afterlife, while those convinced there is nothing beyond death often find motivation in savoring every moment. Western philosophy, from Plato onward, has scrutinized whether an immaterial soul might persist past physical decomposition. Today, materialist schools of thought argue that the mind is merely the electrochemical activity of the brain, so consciousness extinguishes when that activity ceases, like a flame snuffed out. Even so, it remains difficult to define precisely what consciousness is, or to dismiss entirely the possibility that it survives in some form yet unknown. Our inability to achieve either scientific or spiritual consensus on death highlights the enormity of the mystery. Interestingly, this same uncertainty spurs humanity to live more intensely. Not knowing what lies beyond leads many to seek deeper purposes, foster creativity, cultivate meaningful connections, and strive for personal growth. Some futuristic scientific endeavors, cryonics for example, or attempts to transfer consciousness to digital platforms, aspire to bypass or reverse death altogether, though these remain speculative. It's remarkable that despite medical, biological, and neurological progress, our final breath remains a largely unexplored threshold. Some see this ignorance as an invitation to humility, a reminder that we do not know everything and perhaps never will. In a sense, the mystery of death lends life a unique quality. Precisely because life ends, each day carries importance, and maybe that's the real takeaway. Whether there's something beyond the darkness or just a definitive end, we are all, in the end, sailing in the same boat, united by our inability to answer that ultimate question with absolute certainty. Why does the universe exist? Gazing at the night sky can lead us to one of the most profound questions. Why is there something instead of nothing? Modern science proposes that everything observable emerged billions of years ago from what we call the Big Bang, but that explanation addresses how it happened, not why. It traces the steps from a singularity to galaxies and planets, but does not illuminate the ultimate reason a cosmos exists at all. rather than a state of absolute emptiness. One widely discussed theory is that the universe could have arisen from quantum fluctuations. At a fundamental level, vacuum may not be genuine emptiness, but a state with enough energy to spawn particles and antiparticles that form and vanish. A slight disturbance could have triggered the initial expansion we observe in the cosmic microwave background. Yet this view pushes the riddle one step further. Why was there a quantum vacuum in the first place, rather than complete non-existence? Philosophical and theological traditions propose various answers. Some describe a divine creator who consciously set the universe into motion. Others suggest the cosmos might be eternal, cycling through expansions and contractions. A separate view holds that the universe simply is, without deeper cause or rationale. The so-called anthropic principle adds another layer. It posits that we see the universe in this precise form because only such conditions allow life, and thus observers, to emerge. If the universe weren't set up to enable life, nobody could question its existence in the first place. Critics, however, argue this principle does not truly explain why the universe exists. It merely notes that any universe containing observers must permit their existence. Speculation also turns to the multiverse, positing our universe as merely one bubble in a vast cosmic sea of other universes, each governed by different laws. In that scenario, the question of why does something exist dissolves into infinite possibilities. Every conceivable set of conditions might exist somewhere. Yet we currently lack direct evidence for these alternate universes, placing the idea on the theoretical edge. All these concepts may ultimately be more profound than our reasoning can handle. Philosophers often note that the notion of nothingness is problematic. If nothing existed, would it still be nothing? Or does discussing nothing make it something? Language may be inadequate to depict realities that defy everyday experience. Hence the question, why does the universe exist, remains as vibrant now as in ancient times. Curiosity and the search for meaning are part of our nature, and while science continuously refines our understanding of how the cosmos evolves, the fundamental why may remain elusive. Perhaps it lies beyond the reach of scientific methodology, or maybe we require a theoretical revolution we have yet to imagine. Either way, the vastness of the universe and the apparent improbability of our presence within it spark a deep wonder that drives us to keep questioning, seeking, and learning. The hard problem of consciousness. Throughout the day, we experience a non-stop flow of internal sensations. We see colors, taste flavors, feel emotions, and live moments of nostalgia or anticipation. Almost seamlessly, we hold a first-person perspective we call myself. Yet explaining how the brain produces or accompanies that subjective experience is the renowned hard problem that has long intrigued philosophers and scientists. Neuroscience has pinpointed neural correlates of consciousness, activity patterns correlated with specific perceptions. For instance, we know which brain regions light up when we recognize a face or feel pain. However, understanding these correlations does not clarify why such physical processes produce experiences or what transforms raw electrical signals into lived sensations. This is often described as a significant explanatory gap. We comprehend the measurable objective side, but not the subjective, inaccessible side. Philosophers of mind generally cluster into two camps. Materialists claim that everything is physical and that consciousness naturally emerges from sufficiently complex neuronal activity. In principle, an advanced artificial intelligence might become conscious if complexity alone is the key. Dualists, on the other hand, hold that consciousness cannot be purely reduced to physical processes. They propose a separate dimension, sometimes called soul or mind, that does not fit neatly into physical laws. More radical approaches, such as panpsychism, posit that consciousness is a fundamental property of the universe, present even at the level of elementary particles, albeit in very primitive form. Human consciousness would thus be a sophisticated manifestation of something that underlies reality. While this may sound outlandish, it tries to bridge the gap between non-conscious matter and conscious experience by asserting that consciousness never truly emerges from nothing because it was there all along. Historically, religions have interpreted consciousness as a divine spark or non-material essence. No consensus exists, and the hard problem of consciousness encompasses more than physiology or the anatomy of the brain. It addresses the very heart of what it means to have an inner life. Another powerful concept is qualia, referring to the subjective quality of experiences. What red truly looks like to me versus you, for example. We have no way to confirm we experience color identically. Words like red could mask different inner perceptions. This underscores how individualized consciousness is. Future developments might yield technologies capable of stimulating or recording consciousness in novel ways, or possibly uploading experiences. Each new finding in brain research sheds light on parts of the puzzle, yet the core question, why is there a subjective I, remains unanswered. Perhaps it defines a fundamental limit of our investigative tools, or perhaps a breakthrough in theory will reveal consciousness in an utterly new light. The illusion of free will. We often feel we choose freely. Deciding what to wear, what path to take, or when to act seems entirely our call. Yet certain scientific findings cast doubt on how much genuine control we have. Laboratory experiments show that when people are asked to press a button anytime they wish, a distinctive pattern of brain activity appears fractions of a second before they consciously register the desire to press it. Some interpret this as the brain deciding first, while our sense of free choice forms afterward. Such data support the possibility that free will might be an elaborate construct of the mind, contradicting our day-to-day impression that we can spontaneously pick between options. A thoroughly deterministic view goes further, claiming every event is the outcome of prior causes stretching back to the universe's beginning. Under strict determinism, there is no genuine choice, only the unfolding of cause and effect. However, modern physics also reveals quantum indeterminacy, where certain events appear probabilistic rather than strictly determined. Does that open a small window for true free will? Perhaps not, argue some, because randomness is not the same as conscious choice. Others propose more intricate theories, suggesting our minds might interact with quantum phenomena in ways science has yet to confirm. Philosophers ponder the implications for morality and responsibility. If everything is predetermined, does the notion of personal accountability still hold? Many thinkers, known as compatibilists, maintain that free will and determinism can coexist, provided we define free will as acting according to our own internal desires and goals, even if those desires and goals have causes of their own. They stress that freedom is about self-determination rather than escaping causality altogether. Beyond academic debate, the question touches on how we handle justice, ethics, and everyday living. Legal systems presume that people can distinguish right from wrong and choose accordingly. If we discovered free will to be an illusion, would we overhaul our concept of punishment and reward? Some argue that even if freedom is an illusion, it remains a practical one, because societies need to encourage constructive behavior and discourage harm. Introspectively, we experience decision-making as fluid and voluntary. But how trustworthy is that feeling, and might it just be the brain's way of narrating events already in motion? This quandary shows the complexity of the human mind. The line between real and apparent control might be blurrier than we assume. In the end, the true value of this enigma may lie in its power to make us reflect on what being human means and on the foundations of social life. Whether or not free will exists in the ultimate sense, most of us behave as though it does, finding in it a wellspring for creativity, hope, and moral responsibility. Perhaps that utility is enough for many, illusion or not. Before the Big Bang model describes a universe that began as an extremely hot, dense point and has expanded for billions of years to become what we see today. Yet two questions emerge as we trace time backward. Did anything exist before this event, and how can such a notion even make sense if there was no space or time as we understand them? According to general relativity, time is woven into the fabric of the universe itself. As we approach the Big Bang, the equations suggest that time was squeezed to such an extreme that talking about before may be meaningless. Many cosmologists assert that if the Big Bang truly was the origin of space-time, then asking what preceded it is akin to asking what's north of the North Pole. Still, not everyone agrees. Alternative ideas, such as cyclic universe or Big Bounce models, propose that our cosmos might be the expansion phase following a prior collapse. Here, the Big Bang is not an absolute beginning, but rather a bounce from a previous state. Other hypotheses bring in quantum gravity, a realm where neither space nor time behaves as in classical physics. We lack final experimental confirmation for these views, but they illustrate how before the Big Bang might not be an illogical question after all. There's also the multiverse scenario. Perhaps our Big Bang is just one bubble among countless universes within a higher reality. If so, before could lie in that meta-universal realm, something altogether different from space-time. Yet these ideas largely remain untestable through direct observation. Philosophically, this topic intertwines with the deeper question of how existence itself begins. If time and space started at the Big Bang, does that imply the universe created itself? Religions might interject with a divine force outside space-time that initiated creation. None of these suggestions can be definitively proven or disproven at present. Moreover, observational limits prevent us from seeing further back than the cosmic microwave background. Before that epoch, the universe was so dense that light could not travel freely, leaving us with a kind of curtain. As a result, verifying any theory about before is extremely challenging. In sum, asking about what preceded the Big Bang nudges us to the edge of known physics and perhaps of language itself. We mix cutting-edge cosmological equations with metaphysical speculation and remain uncertain. Future discoveries, maybe a complete quantum gravity theory, could bring clarity, or we might find this question lies forever beyond human grasp. Either way, it's a striking example of how the cosmos keeps its deepest beginnings shrouded in mystery. Simulation theory. For centuries, thinkers have questioned whether the world we perceive is genuine or an illusion, as illustrated by Plato's allegory of the cave or Descartes' "I think, therefore I am." In the digital age, these doubts have evolved into the suggestion that reality could be an immense computer simulation, possibly running on some advanced civilization system while we remain unaware we're simulated beings. The modern simulation argument hinges on the premise that a civilization far more technologically developed than ours might have enough computing power to simulate entire universes in meticulous detail. Given how computing power has soared, some philosophers and scientists speculate that eventually creating fully simulated universes might be quite feasible. If that future scenario occurs, one might assume that hundreds, thousands, or even millions of such simulations would run. Statistically then, the chance of living in the original universe is vastly smaller than living in a simulation. At first glance, this resembles science fiction, but it becomes more thought-provoking when we consider our own advancements in virtual reality and AI. Though we're nowhere near simulating the entire cosmos, exponential progress prompts us to wonder what could be possible in a few centuries or millennia. A core problem, however, is proof. How would we detect a simulation if the programmers were skilled enough to hide any telltale errors? Some theorists propose that peculiar quantum behaviors, like particle-wave duality or entanglement, might be clues to an underlying code. So far, no conclusive glitch or matrix-like failure has emerged as definitive evidence. If we were in a simulation, it's unclear what the creator's motive would be. They could be scientists from a higher-level universe simply running a grand experiment. Perhaps they seek entertainment, or maybe we ourselves in the far future are simulating our ancestral past. These speculations echo debates about God or gods. Are we governed by superior beings? The simulation theory reframes that ancient idea in tech-centric terms. Despite its popularity, simulation theory remains purely speculative. Its proponents argue it cannot be easily dismissed, yet critics note it makes no testable predictions and lacks a transparent verification strategy. Furthermore, the possibility of infinite nested simulations arises. If our reality is simulated, might we in turn simulate another universe, and so on? Would any of this alter our daily lives? Probably not. We still have to eat, form relationships, and seek meaning. A well-crafted simulation would likely be impervious to sabotage from within, making it almost impossible for us to break out. Hence, some see simulation theory as an intriguing philosophical puzzle, but with minimal practical effect. For now, there's no strong evidence we inhabit a cosmic computer program. Still, pondering the possibility underlines how fragile our concept of real can be, reminding us we rely on our senses and rational thinking to navigate life. The very notion that we might be lines of code serves as a testament to how far our pursuit of truth can push us, even to question the fundamentals of existence. The fate of the universe. On a clear night, the starry vault may seem peaceful and unchanging. Yet modern astronomy reveals that the universe is anything but static. Galaxies recede from each other under the accelerating push of dark energy. This cosmic expansion leads to pondering the possible endings of everything. One widely supported scenario is called the Big Freeze, or heat death. It posits that expansion will continue indefinitely, dispersing matter and energy so thinly that stars burn out, galaxies drift apart, and all activity fizzles in an ever colder expanse. This is a silent end, where entropy reaches its maximum and the cosmos becomes inert. An alternative is the Big Crunch. Here, the total mass energy of the universe might eventually overcome the expansion's momentum, reversing it until everything collapses back into a super-dense state akin to the Big Bang. That implosion could theoretically repeat in cycles, but current data about accelerated expansion makes this scenario seem less likely. The Big Rip is another possibility, more catastrophic than the others. If dark energy grows strong enough, it could not only separate galaxies but tear apart stars, planets, and ultimately the space-time fabric itself. Matter would be shredded at every level, bringing a violently abrupt finale. Which outcome wins depends on factors like how dark energy behaves over time, the total density of matter, and other cosmic parameters. Astronomical observations, especially from distant supernovae and the cosmic microwave background, keep refining these models, though no single fate has unanimous backing. Philosophically, the universe's possible demise raises existential questions. If it all ends in darkness or devastation, does our existence carry meaning? Could life emerge again eons in the future, or is our era the sole window for living complexity? Some cyclical universe theories imply endless rebirth. Others point to a permanent ending that underscores the transience of all things. Spiritual and religious traditions have long contemplated apocalyptic or eschatological scenarios, typically more symbolic than scientific. For practical purposes, humanity has billions of years to exist before cosmic expansions become truly inhospitable. Nevertheless, reflecting on a possible cosmic finale can encourage a humbling perspective on our place in the vastness of time. It's remarkable to realize that something so colossal and ancient is evolving with a certain direction, potentially leading to a quiet hush or a violent tear. While we may never witness it firsthand, speculating about the universe's future highlights the impermanence woven into every corner of reality. It also sparks gratitude. Our present moment of cosmic vibrancy with planets, stars, and life is a fleeting chapter in a grand cosmic narrative. The mystery of gravity. Every day, we deal with gravity. It keeps our feet on the ground, governs falling objects, and binds the moon to Earth. We learn to live with it from infancy, yet fully understanding it is astonishingly tricky. Isaac Newton conceived it as an attractive force acting at a distance without any tangible medium to transmit it, which left a conceptual gap. Albert Einstein took a revolutionary step by explaining gravity as the curvature of space-time, rather than a conventional force. According to his general relativity, massive objects warp the fabric around them, guiding how other bodies move. Earth orbits the Sun because it follows the curve produced by the Sun's mass. This framework masterfully explains phenomena like Mercury's orbital shift and the bending of starlight passing near the Sun. However, there is another crucial piece in the physics puzzle: quantum mechanics, which excels at describing the subatomic realm. Relativity handles huge scales, galaxies, black holes, whereas quantum physics rules the tiny world of particles. The problem? When you try to apply both theories in extreme conditions, like the heart of a black hole or the universe's birth, they conflict. Scientists have spent decades searching for a quantum gravity theory, but it remains elusive. Some hypothesize a graviton, the particle that would mediate gravitational effects in the quantum domain, akin to how the photon mediates electromagnetism. Yet no direct evidence of gravitons has emerged from particle accelerators or cosmic observations. Other proposals involve string theory or loop quantum gravity, each striving to bridge the gap. Gravity also plays a central role in cosmic structure. It sculpts galaxies, drives star formation, and orchestrates the dance of planets. It interweaves with dark matter, invisible but providing extra gravitational pull, and dark energy, fueling accelerated expansion. This invisible tug-of-war shapes the destiny of the universe, so comprehending gravity's essence might lead to breakthroughs about our cosmic fate. Some researchers suspect we might need to revamp either relativity or quantum theory, or both, to unify them under a new paradigm. Others suspect discovering how gravity fits into the quantum realm could unravel secrets about black holes, the earliest moments of the universe, or phenomena we haven't even imagined. That such a familiar force is still steeped in mystery underscores how much we have yet to learn. With each step, jump, or object we drop, we experience something so fundamental and yet not fully explained. Far from a limitation, this fuels our awe. We live daily with one of nature's cornerstones, oblivious to its deeper workings. Perhaps that is an invitation to explore more deeply and never take the mundane for granted. Dark matter. Studying galaxies in clusters, astrophysicist Vera Rubin noticed that stars at their edges moved at speeds that defied Newtonian calculations based on visible matter alone. If only normal mass were present, those stars should fling off into space, yet they don't, implying something unseen is holding them together, a substance that came to be called dark matter. The enormity of the problem is striking. Scientists estimate that roughly 85% of the universe's total matter is dark matter, while the ordinary atoms making up planets, stars, and everything we see comprise only a small fraction. How can the bulk of all matter remain effectively invisible? Researchers around the world have been searching for it in underground labs and space-based detectors, but so far there is no definitive result. Several hypotheses attempt to identify dark matter's composition. One popular idea points to WIMPs, weakly interacting massive particles, which rarely interact with regular matter except through gravity and possibly the weak nuclear force. Others propose axions arising from theoretical solutions to puzzles in quantum chromodynamics. There are also alternative gravity theories like MOND, suggesting that maybe our understanding of gravity is incomplete at large scales, though these are less accepted. Dark matter also appears vital to cosmic evolution. In the early universe, its gravitational pull likely played a major role in clustering gas and dust to form stars and galaxies. Without that scaffolding, structures might have taken far longer to emerge, if at all. Additional evidence comes from gravitational lensing. Light from distant galaxies is bent by massive objects along its path. Astronomers notice distortions more extreme than expected from visible matter alone. The cosmic microwave background also carries signatures hinting at dark matter's presence. Despite the extensive efforts and sophisticated experiments, dark matter has yet to be directly detected. Each year sees new detectors or revised methods, from searching for unusual particle collisions in the Large Hadron Collider to installing ever more sensitive instruments underground to minimize interference. Finding even a single shred of conclusive evidence could be transformative, ushering in a new era of physics that stretches beyond the standard model. Some argue our concepts of matter and energy are still too narrow. Past revolutions, relativity, quantum mechanics, cosmic expansion, once seemed impossible until they became established facts. Perhaps unveiling dark matter will spark another seismic shift, revealing properties we never anticipated. Until then, each galaxy quietly reminds us of a massive unknown. Most of what shapes them remains undetected, a cosmic shadow we can only infer by its gravitational footprint. The mere fact that something so central to the universe eludes direct observation challenges our confidence and calls for humility in the face of the cosmos's immensity and mystery. Dark energy. Once we learned the universe was expanding, the logical assumption was that gravity would slow the expansion over time. In the late 1990s, however, observations of distant supernovae revealed the opposite. The expansion is speeding up. Scientists labeled the mysterious force driving this acceleration dark energy, an enigmatic term that highlights how little we actually know. By current estimates, about 68% of the total energy content of the universe is tied up in dark energy, surpassing even dark matter, about 27%, and ordinary matter, around 5%. Put plainly, the majority of the cosmos is something we cannot touch or see, yet it shapes our future on the grandest scale. Einstein had introduced a similar idea through his cosmological constant, a term in his relativity equations meant to keep the universe static. After Hubble's discovery of expansion, Einstein called it his greatest blunder. Yet now that constant is once more a candidate to explain dark energy, a property of the vacuum of space-time that yields negative pressure, pushing the universe outward. There are other contenders. Some scientists posit a dynamic field called quintessence, which could vary over time and space. If so, the fate of the universe depends on how this field evolves. As yet, no direct measurement confirms such a field's existence. Dark energy underpins modern cosmological models, clarifying why galaxies recede from us at speeds that increase with distance. It also leaves imprints in the cosmic microwave background and the large-scale arrangement of galaxies. Still, the concept remains largely theoretical. For many researchers, decoding dark energy and thereby understanding the cosmological constant could spark a revolution akin to that of quantum mechanics or relativity. The so-called cosmological constant problem underlines the struggle. Quantum theory predicts a vacuum energy far larger than what we observe, a mismatch of many orders of magnitude. Reconciling this might necessitate groundbreaking insights into the nature of space, time, and energy. What's so striking is that dark energy effectively decides the universe's destiny. If it remains constant, a perpetually expanding, cooling cosmos lies ahead. If it grows, a more drastic end like the Big Rip may occur. In either case, we see a dynamic universe that upends any notion of a static cosmic scene. As with dark matter, our lack of clarity regarding dark energy highlights how our best theories can fall short when confronted with reality's hidden facets. It shows that an entire section of the cosmos remains outside our grasp. Each new observation invites us further into the unknown, revealing that, despite centuries of scientific advancement, we are still novices in a universe whose vast majority continues to mystify us. The nature of consciousness, the question, what is consciousness, delves beyond the hard problem of how it arises, scrutinizing whether consciousness is purely biological or might take other forms. Many hold that consciousness depends on brain activity. Without a functioning brain, there is no perception, memory, or feeling. Yet others, including certain spiritual viewpoints, argue that consciousness is irreducible and cannot be explained merely by chemistry. Debates on the nature of consciousness explore whether it's an emergent property of complex matter or a fundamental component of reality, as panpsychism suggests. In the latter view, everything has some degree of awareness, no matter how minuscule, so human consciousness would be a heightened version of a universal property. While this theory may sound fanciful, it tries to solve the puzzling jump from non-conscious to conscious states by asserting that consciousness was always present. An alternative stance declares consciousness might be an illusion, and that what we call the conscious mind is simply a post hoc commentary on unconscious processes. Yet each of us who experiences being conscious can't deny that it feels real. This tension between an external scientific perspective and the internal, undeniably real perspective captures the essence of the enigma. Whether non-biological systems could develop consciousness is another issue. Could a sufficiently advanced AI become self-aware? There's no consensus, but the notion forces us to ask what separates a genuinely conscious being from a highly efficient processor of information. The challenge intensifies when we try to define consciousness without falling into circular reasoning. We say it's the capacity for subjective experience, but to observe that capacity, we rely on conscious observers. Then there are altered states of consciousness, dreams, deep meditation, psychedelic journeys, where the nature of experience radically shifts. Some spiritual traditions argue these states reveal other dimensions or deeper truths, while neuroscientists see them as dramatic alterations in brain function, illustrating the mind's plasticity. Ethical implications abound. If consciousness might emerge at different levels or in different substrates, how should we treat animals or even potential synthetic minds? Could the cosmos itself harbor a global consciousness? Some holistic models claim the entire universe has some awareness of itself. Ultimately, the nature of consciousness circles back to who we are and where we stand in reality's grand design. If matter and energy are all there is, and consciousness arises from them, we are a remarkable side effect of cosmic evolution. But if consciousness is its own dimension, we might be missing a critical piece of the puzzle. With numerous angles from science, philosophy, and spirituality, the conversation evolves with each new finding, yet the mystery endures, perhaps because consciousness, trying to examine itself, meets intrinsic limitations. We are both the observer and the observed, a self-referential loop that lays bare the boundaries of understanding. Quantum versus relativity. Two theoretical giants prop up modern physics, general relativity and quantum mechanics. Each has been experimentally validated with astonishing precision in its respective realm. Relativity clarifies how matter and energy warp space-time, revealing cosmic phenomena such as gravitational lensing, black holes, and the orbits of heavenly bodies. Quantum mechanics, meanwhile, governs atoms and subatomic particles, showing how they exist in superpositions or become entangled across distances. The trouble arises when trying to apply these frameworks simultaneously in extreme conditions, like the center of a black hole or the universe's earliest moment. There, you need relativity's handling of intense gravity along with quantum theory's laws of the very small. Merging them leads to mathematical inconsistencies, infinities that cannot be neatly removed. Physicists have tried for decades to reconcile the two. Ideas like string theory imagine every particle as a tiny vibrating string in a higher dimensional space, potentially unifying all forces including gravity. Others champion loop quantum gravity, seeing space-time as a network of discrete loops at microscopic scales. Yet none of these theories has found unambiguous experimental support, leaving the door wide open. Why is unifying the two so hard? Part of it is conceptual. Relativity is geometric, deterministic, and continuous, whereas quantum mechanics is probabilistic, dealing in discrete quantities. In quantum field theory, you can renormalize away problematic infinities for forces like electromagnetism, but gravity stubbornly resists such methods. An additional conflict arises around information. Quantum mechanics holds that information about a system is never destroyed, but in relativity, it seems that information can vanish into black holes, an apparent clash known as the black hole information paradox. Researchers keep pushing for a resolution that might reveal how black holes handle quantum data. Many suspect that only observations of extreme phenomena, perhaps gravitational waves carrying quantum signatures, or particles emerging from black hole evaporation, Hawking radiation, might confirm which path to unification is correct. Technological leaps or unexpected experimental hints could push one theory ahead. Meanwhile, the split between quantum mechanics and relativity underscores how our best descriptions of the universe remain incomplete. Each elegantly addresses a portion of reality, large versus small, but yields contradictions in overlapping domains. Resolving this may bring us a theory of everything, a revolutionary new horizon that, like Einstein's or quantum revolutions of the 20th century, could alter our sense of what's real. The reality of time. Time feels so obvious, a river flowing from past to future, with each second ticking by uniformly. Yet physics and philosophy have deeply challenged that assumption. Einstein's relativity shows that time is not absolute. It can stretch or contract depending on velocity or gravitational strength. So an astronaut traveling at high speed might only age 5 years while a friend on Earth ages 10. Furthermore, some theorists propose a block universe model in which past, present and future all coexist in a 4-dimensional structure, and our experience of now is just how consciousness slices through that structure. Under this viewpoint, time's passage might be an illusion generated by the mind, meaning the future might already be there, though we haven't subjectively reached it. Quantum mechanics adds further twists. Certain experiments hint that the order of events can be ambiguous depending on reference frames. All of this reinforces the idea that time is not a universal backdrop but can vary based on observation and context. Outside of physics, we notice how subjective time can be. It crawls when we're bored and races when we're busy or immersed in novelty. Some attribute this to how the brain encodes memories. A child's day, packed with new experiences, feels longer. As adults settle into routines, months or years may appear to fly by. Philosophically, we wonder if time truly exists out there, or if it's merely a conceptual tool our minds impose. Immanuel Kant argued that time and space might be mental frameworks, not necessarily things in themselves. Others insist time is very real, crucial to how matter and energy unfold. These possibilities intersect with debates about free will. If the future already exists, is our sense of choice illusory? If the past remains preserved in the block universe, then nothing is truly lost. Yet, how does that reconcile with our everyday notion of moving forward? Day to day, we still track our schedules, measure hours, and plan for tomorrow. But awareness of time's flexible, possibly illusory nature can shift our perspective. It reminds us that aspects of our perceived world may hinge on a vantage point that is itself shaped by mind and circumstance. Time endures as one of the grand enigmas, revealing as much about our inner experiences as it does about the outer cosmos. Multiple consciousnesses. We typically identify with one continuous stream of thought, our internal voice that seems unified. Yet neurological evidence suggests the brain may house several modules or agents working concurrently. Rare cases such as split-brain patients, where the corpus callosum connecting the two hemispheres is severed, reveal scenarios in which each hemisphere can act on distinct information, sometimes with clashing motives or perceptions. This sparks the notion that the mind might be a collection of processes that collaborate, and sometimes compete, to produce the unified sense of self we normally experience. Michael Gazzaniga's interpreter theory posits that one part of the brain weaves these processes into a coherent story. That coherence might be superficial, masking a deeper multiplicity. A more dramatic example is dissociative identity disorder, formerly known as multiple personality disorder. Individuals may report separate identities within one body, each with its own memories and traits. Although the causes and diagnosis remain debated, such accounts reinforce the idea that the mind can fragment into distinct centers of awareness. The modular mind hypothesis in evolutionary psychology suggests specialized neural modules for language, vision, social decision-making that usually coordinate smoothly. However, if something disrupts that coordination, do we see glimpses of parallel consciousnesses? For most of us, it appears as internal conflict. Part of us wants one thing, another part hesitates. We don't label them separate selves, but that might be a matter of degree. This leads to philosophical questions about identity. If the mind can split under certain conditions, is the classical notion of an indivisible soul tenable? It also touches on moral and legal concerns. If decisions emerge from multiple subagents, who is truly accountable? In AI research, some propose building advanced systems akin to the human brain, with modules that operate semi-independently and then unify into a single intelligence. Such designs raise the possibility that an AI could develop multiple eyes or unify them, just as the human brain seemingly does. Ultimately, contemplating multiple consciousnesses revamps our view of selfhood. It hints that consciousness isn't a monolith, but perhaps an orchestration of countless neural voices. Generally, these voices sync so effectively that we believe we are one consistent entity. Yet, illusions, disorders, and neurological cases remind us that unity may be more fragile and intricate than we suspect, a delicate balance of processes forging a singular consciousness out of many. How memory works. Recalling an old childhood moment isn't like pressing play on a perfectly recorded video. It's a reconstructive process, blending raw traces of the original event with your current state of mind, new information, and evolving perspectives. This explains how two people who share the same experience can have very different recollections, and why you might recall the same event in differing ways over time. The brain stores information within distributed neural networks. Specific clusters of neurons encode an experience's elements: a friend's face, the sound of their laugh, the setting in which you met. Recalling that friend reactivates parts of those networks, but each retrieval subtly reshapes those connections, creating the potential for distortions. We categorize memory into different types. Working or short-term memory maintains info temporarily, like a phone number you'll dial right away. Long-term memory can be declarative, facts, names, events, or non-declarative, skills, habits, emotional responses. Each type involves distinct brain circuits, with the hippocampus vital for consolidating long-term, declarative memories. On a molecular level, the durability of memories depends on synaptic plasticity, the strengthening or weakening of connections between neurons. Specific proteins can enhance or stabilize these connections, yet the full mechanism for how the brain permanently houses memories for decades is still being unraveled. Forgetting isn't merely a glitch, but often a useful feature. Retaining every detail can overload the brain. We generally keep emotionally significant or frequently rehearsed information, discarding what seems less critical. Though sometimes we forget important things or store inaccurate versions, the process remains an adaptive trade-off. Memory failures take many forms: retrograde amnesia, losing past memories, or anterograde amnesia, struggling to form new memories, as seen in patient HM's subtler errors, include false memories that can be implanted through suggestion. Studies show how easily we can come to believe we experienced events that never really happened, with serious implications in contexts like eyewitness testimony. Researchers also explore ways to improve memory, from learning techniques like spaced repetition to experimental drugs that boost consolidation. But heightened memory might have drawbacks if it cements painful or trivial recollections. Balancing what we remember and what we let go can be crucial for mental well-being. Modern brain imaging allows us to observe memory processes in real time, adding to our understanding of the where and how of retrieval. Yet it's clear we're just scratching the surface of this intricate phenomenon. After all, our identities lean heavily on what we recall, and the dynamic, sometimes fallible nature of memory is a core thread in our personal narratives. Far from a mere archive, memory shapes our sense of self, bridging past, present, and future in an ever-evolving tapestry. The origin of life. Earth teems with millions of life forms, all seemingly descended from primitive organisms that emerged roughly 3.8 billion years ago. How did a once barren planet, rife with volcanic activity, transform into a living world? The question remains unresolved, though multiple theories exist, ranging from a chemical primordial soup to hydrothermal vents in the ocean depths, or even extraterrestrial seeding from comets. One of the iconic experiments addressing life's origins was the 1953 Miller-Urey setup, which simulated a primordial atmosphere containing methane, ammonia, hydrogen, along with electrical sparks for lightning. After several days, the solution yielded amino acids, the basic components of proteins. This didn't result in fully formed cells, but it demonstrated that simple organic molecules could spontaneously arise under plausible early Earth conditions. Subsequent theories focus on molecules capable of self-replication, such as RNA, which might have served as both genetic material and a catalyst. Over time, these molecules could have become enclosed in lipid membranes, creating protocells that eventually developed into true cells. Yet the exact transition from inorganic chemistry to complex self-replicating life remains elusive. No lab experiment has replicated that leap in its entirety. Panspermia is another intriguing hypothesis, suggesting life arrived via meteors or comets, carrying organic compounds or microbes from elsewhere in space. Certain extremophiles on Earth do survive harsh environments, but no direct evidence confirms they traveled cosmic distances to colonize our planet. Moreover, even if life did land here from afar, we'd merely shift the question to how it started out there. Other researchers highlight deep-sea hydrothermal vents. These underwater chimneys spew mineral-rich, superheated water, potentially creating chemical gradients that promote complex reactions. Entire ecosystems thrive around these vents, relying on chemosynthesis rather than photosynthesis, thus underscoring the possibility that life could have begun in such environments. Whatever the exact origin, once the first self-replicating entities emerged, natural selection and genetic mutation took over. Across millions of years, they evolved into the wondrous diversity we observe. The fossil record indicates the earliest known cells were simple, akin to bacteria, with more complex eukaryotes arising later, eventually giving rise to multicellular organisms and the explosion of life forms populating land, sea, and air. If we ever fully unravel how life originates, it might enable us to pinpoint biosignatures on distant planets. Finding life in another corner of the universe is a driving force for space missions investigating Mars, icy moons like Europa or Enceladus, and exoplanets' atmospheric signatures. So far, no detection of extraterrestrial life has been confirmed, but each technological breakthrough nudges us closer to understanding how widespread life may be. The central debate remains whether life is a rare accident or nearly inevitable under the right conditions. Should evidence of life be found elsewhere, it could imply the cosmos is awash with living systems. If not, Earth might be a singular oasis in a vast cosmic sea. Either scenario is awe-inspiring, and the quest to decipher life's origin is a testament to humanity's drive to trace our roots and explore possibilities that lie beyond our world. Physical constants. The cosmos operates under laws that rely on fundamental constants, such as the speed of light, c, the universal gravitational constant, g, Planck's constant, h, or the electron's charge, e. These values, to the best of our knowledge, do not change. Strikingly, even minute deviations could lead to a radically different universe, perhaps one where stars never form or chemistry can't sustain life. This fine-tuning prompts many to invoke the anthropic principle. We observe the universe in this particular configuration because if it weren't suited to life, no observers would exist to notice. But that doesn't explain whether these constants were chosen somehow, or if there exist countless other universes with varying constants. That latter concept is part of multiverse theories, suggesting ours is just one bubble where conditions happen to allow life. Standard physics has measured these constants to extraordinary precision across vast distances and epochs, finding no meaningful variation. Still, the door isn't fully closed on the possibility of slight changes detectable over cosmic timescales. Observations of distant quasars and spectral lines test for shifts in certain constants, but results remain inconclusive. Another idea is that these fundamental numbers could arise from a deeper theory yet to be discovered. They might not be fundamental at all, but derived parameters of a more all-encompassing framework. Perhaps a complete theory of quantum gravity, or a theory of everything, will explain why C, G, and others take specific values. The startling exactness of these constants resonates beyond science and into philosophy and theology. Proponents of intelligent design point to such precision as evidence of a creator's hand, while others argue that in an infinite cosmic lottery, it's no surprise that some universes have the winning combination for life. Since only in those universes would conscious observers arise, there's a built-in observational bias. Experimentally, cosmologists verify these constants' uniformity by examining spectra of atoms in galaxies billions of light-years away. If, for instance, the fine structure constant varied significantly, the absorption or emission lines would shift. So far, data align with it being the same everywhere, reinforcing our sense of a stable cosmic code. Yet the question remains, why these numbers and not others? It stands as a grand challenge, reminiscent of other historical shifts when a new theoretical insight exposed deeper layers of reality. A future breakthrough might reveal how the constants interlock, or even that they are mere manifestations of something else entirely. For now, these constants sustain our current understanding of physics, forming the bedrock of equations that we rely on to navigate everything from particle collisions to cosmological models. Contemplating them underscores how, despite our progress, key pieces of the puzzle remain undiscovered. The universe, it appears, reserves the right to keep certain secrets until we're ready to uncover them, or perhaps indefinitely.